Right, hi everyone, welcome to our synchronous machines tutorial. And we have 4 questions, I believe, to go through. We didn't get a chance to meet today because of the network problems throughout the country. So I'm doing this recording so you all can follow it in your own time. So first up, we have a three-phase 13.8 kV 60 Hz star-connected synchronous generator connected to an infinite bus bar. The synchronous impedance of the machine is J10.55 ohms per phase, and when the excitation voltage is 18 kV, the generator is supplying load to the 13.8 kV bus bar at unity power factor. So as always, the first thing we want to do is draw a diagram of the system. So we have um, we have our synchronous machine here. Let me just increase the size of this. Good. So we have our synchronous machine here that is delivering power to an infinite bus bar 13.8 kV, and we have here 18 kV and J 10.55 ohms. Now, of course, the first thing we have to remember is that the values given here, if they are not specified line to line or phase voltages, they're always line to line voltages. And our diagrams are phase voltage diagrams, they're per phase equivalents. So this would be 13.8 on square root 3, and this would be 18 on square root 3 in the um, in the diagram, in the per phase diagram. So the first thing we want to do is calculate the current and load angle for the condition. So it says that we are generating at a unity power factor. So the first thing we want to do is to draw our power triangle, another power triangle or phasor diagram. So we always start with VT, and if we are delivering at unity power factor, then I would be in the same direction. So of course, when we are generating, the current will go this way from the source into the bus, right? So we have I here, and we have IAXS, which is the voltage drop this way, which is going to be at 90 degrees from I, which will be here. Good. And of course, in this format, with the current going in this direction, we could write the equation EF is equal to VT, which is this voltage here, plus IA by XS. So VT plus IAXS is equal to EF. This is what we have here. So we want to find out what is the current and the load angle for this condition. So let me just increase the size of this diagram here. Right, and now we can see from our diagram, we know what EF is, we know what VT is, we know what XS is, so we can work out the magnitude of IA. So we know that IA XS is equal to the square root of EF squared minus VT squared. That is only because this forms a right angle triangle. If this was not unity power factor, then this angle here would not be at 90 degrees, and we could not use this formula. So only because it is a 90-degree right angle triangle that we could do this. So we have we can solve now for IAXS, and then IA will be all of this on XS, and that gives us the magnitude of IA as 632.45 amps. And this is both the magnitude and the complex value, because of course the angle of IA is 0 because it is a unity power factor. So next up, we have to find the load angle. So the load angle is this angle here, which is the angle between EF and VT, which is delta. So we are going to find that angle. Again, it's very simple. We could just use the cosine rule, and we could say, well, not the cosine rule, but we could use the cosine relationship. Delta is equal to cosine inverse of VT on EF, and that works out to about 39.9 degrees. And that's the end of the first part. For the second part, we want to maintain the power output at the same level, and we want to reduce the power factor to 0.85 lag. And again, we want to find the new current, and we want to find the new excitation voltage. So to firstly go about finding the new current, we have to find the power. So we know the power, let's call it P old for the old value of power, or let's just call it P because it is we're keeping the value of power the same. So P is equal to VT multiplied by IA, the magnitude of these, by cosine of theta. Now initially cosine theta is a 1 because the angle is 0. Cosine of 0 is 1. So when we work out this, we should get about 5.04 megawatts. Now we want to keep this power the same, and we want to change the power factor. So we want a new power factor of 0.85, same power, same terminal voltage. What is the new current? So in that case, we could work out the new current as just IA divided by 0.85. Right, so IA divided by 0.85. Why is that? So we have P is equal to VT by IA nu by, this is cosine theta nu, which is equal to 0.85. So that is VT IA nu by 0.85. So before we were multiplying it by 1. So now we have 0.85. So if you want to bring it back to 1, this could go to 0.85 here. And then we would get the same value. This would cancel with this to give us 1. So we have IA nu, or the magnitude of IA nu is equal to IA over 0.85. And that gives us about 744.1 amps. Now, this is not angle 0 because we have now a power factor of 0.85. So we have to get the complex value. So let's look at what the diagram looks like. We have VT, and now we have a lagging power factor of 0.85. So we have IA somewhere here with our angle theta. So the angle theta is negative. So if we want to find the complex value, IA, that will be equal to the magnitude of IA multiplied by cosine of negative theta plus J sine negative theta. Good? So that works out to be an angle of approximately 31.78 degrees. So, and of course it will be negative. So that is the complex value. And now we know the thing is still generating. We need to find the new EF. And of course, we still have our circuit. We have our value here, 13.8 on root 3. And we know the current now is flowing here is 744 angle minus 31.79. Right, we get 79. And we want to find EF. We know EF is equal to VT plus IAXS. We have IA, we have XS, we have VT. So we add up all these together and we get the answer, which is 13.82 angle 28.87 degrees, because this is kV, right? Good. So let's move on now to number 3. Okay, so I have number 3 set up here. We have 1000 kVA, 11 kV, 3-phase Y-connected synchronous motor with a 10 ohm synchronous reactance and a negligible armature resistance. Calculate the induced voltage when the motor takes 1000 kVA at these varying power factors. So you'll see we're going to do the same thing and just vary the value of the power factor. So I have it here in MATLAB. We're going to essentially do the same thing we've been doing all the time, which is start off with our diagram. So it's a motor this time. So we have our EF, our synchronous reactance of 10 ohms, 11 kV. So it's an 11 kV motor. Remember, the voltage value of the motor is always the terminal value. So this is 11 on square root 3. Again, remember, because the values given are the per phase values, the line to line values, and these are per phase diagrams. And we have EF here. Good. So these values given for the kVAs are 3-phase values. So we need to find the single phase equivalent values for the power in order to find the correct currents and so on. So let's see, first we have here define our 3-phase power, our line-to-line voltage. We found the terminal voltage here, per phase voltage. And we are going to first look at 0.8 power factor lag. So this is motoring. So the diagram for it, we have VT. And if it's motoring, then we have to remember that the electrical system is going to be pulling along the mechanical system. So EF is going to be somewhere below here, right? And our equation here now for motoring, the electrical system is pushing current into the motor. So arrows are going to go like this, and we're going to get VT is equal to EF plus IAXS. So we have a lagging power factor. So this means that the current is going to lag the voltage. So the current is going to be somewhere down here, which means our IAXS is going to be in this direction here. Good. So EF plus IAXS, if we draw IAXS to finish on VT, IAXS, our EF will be somewhere here. So this is the situation that we have. Let me make that a little bit neater. Good. So that is the situation that we have. And we want to now calculate the induced voltage. So we have to calculate EF for these various conditions. So the first thing we're going to do is we're going to find IA, because we have VT, we have XS. If we find IA, we could simply get EF is equal to VT minus IA XS. So we have VT, we have XS, we need to find IA in order to find EF. So how do we find IA? Well, we know that the magnitude of IA determines the power. So we have S, which is 1000 kVA, and we know S is equal to VI. The magnitude of S is equal to the magnitude of V by the magnitude of I. This comes from S is equal to VI conjugate, right? But we just need the magnitude here. We could actually do it with the angle as well, because we have the power factor angle. So we could get the power factor, the angle of S, or we could put in the angle after, because it is the angle of I, the angle of I, the angle of S is the same angle. So let's take it with getting the magnitudes first. So S here would be 1000 kVA on 3. This is because it is per phase, and the power given was the three-phase power, is equal to V, which is 11 K on root 3 by I. So when we work out the magnitude of I, that works out here, magnitude of I is equal to 52.47 amps. But we want the complex value of I, because this is a vector equation that we're trying to solve here, right? Remember, I here has some direction, so we can't just use the magnitude. So we want to get the complex value of I. So we have I is equal to the magnitude of I multiplied by, again, we need negative theta because it is lagging, cosine negative theta plus j sine negative theta, right? And that gives us 41.99 minus j 31.49 amps. And then we can simply plug that into our equation. EF is equal to VT minus IA XS. Now we have VT, we have IA, and we have XS, and that gives us EF as 6.05. This is, I have it worked out here, 6.05 K angle negative 3.98 degrees. Good. So you'll see it worked out with EF being negative, just as we have in our diagram. And this is essentially the same process you're going to go through for all the different ones, right? So let's look at those. For all of them, for unity power factor, you'll see that the same process. We have PF 0.8 here. We find the magnitude in each case. So it's the same magnitude. And all we're doing is we're changing the value of theta. So theta is going to change according to the power factor. And then we go through the same process of getting the complex value of I, and then doing VT minus IA by JXS. Good. So you could do that for all the different ones, for 0.8 lag, for unity power factor, for 0.8 lead. So how does 0.8 lead differ from 0.8 lag? If we have a leading power factor, you're going to have VT here, and then IA will be this way. If IA is this way, IA XS is going to be here. So we're going to have EF way down here, right? So EF is going to be larger. So, um, so how does that translate? If this is I here, it means that theta is just positive. That is what it turns into. So unity power factor doesn't matter, negative theta or positive theta. The value of theta is 0, the arc cos of 1. So it doesn't matter what you put it as there. For the leading power factor, you see that the value of theta is positive, right? Because the current is leading. But the process is more or less the same. Good. And that is the end of the next question. So of this question, so we'll go to question 4 next. All right, so the next question, here we have a 6-pole permanent magnet synchronous motor driven by a 3-phase 480 volt 50 Hz sinusoidal source, and the synchronous reactance of the motor is 0.5 ohms with an induced voltage of 400 volts. The motor drives a constant torque load of 2000 Newton meters, and you have to determine the power angle and the power factor at the motor terminals. So again, we're going to start by drawing our diagram. So this is a motor. So we are going to have the current coming in this way, driven from the electrical side, 480 on square root 3. Remember your square root 3. And here we have 400 on square root 3. And we have J 0.5. Good. So we know our equation governing this circuit is Vt is equal to EF plus IAXS, right? So, right, so now we need to find the power angle delta given the given all this here, the torque and so on, and the poles and all of that. So we have this equation, T, the torque is equal to 3 Vt EF over omega xs by psi delta. We know the torque is 2000, we know Vt, we know EF, we know xs, we know omega. But how do we find omega? And this is, of course, important. We need, it's not just converting straight from the frequency to RPM. We have to take into consideration the pole pairs. Remember, the pole pairs relate the number of electrical cycles to the number of mechanical revolutions, right? So if, for example, we had the rotor and we had one pole pair, an electrical cycle, right? If we have north here and south, an electrical cycle happens when we go from north through south back to a north pole. It doesn't matter which north pole, from north to south, south to north. So if we have two poles, which is one pole pair, then you go north, south, north, you get one electrical cycle. So you have one electrical cycle is equal to one mechanical revolution. If you have two pole pairs, so we have now north, south, south, north. So we have north, south, north, south. Sorry, right? North, south, north, south. So what we're going to get is north to south to north will give us one electrical cycle. Then north to south to north will give us two electrical cycles. So two electrical cycles is equal to one mechanical cycle. So the increase in the pole pairs effectively slows down the motor. So you can have the same frequency of supply, and if you add pole pairs, you're going to slow down the motor. And you'll see here, that is why the omega is given by 2 pi f on the number of pole pairs. So 2 pi f on number of pole pairs, that is the radians on the number of pole pairs. We get 104.72 radians per second. So we have all the things here, so we could simply find delta here as sine inverse of all of this, t omega xs on 3 vt ef, and then we will get the value of delta, which works out to be 33 degrees. Now we need to find the power factor at the motor terminals. So we know Vt in this case, which is our 480 on root 3. We know the value of EF, and we know what delta is. So delta is 33 degrees, but what direction is it in? So to know that, we have to look at what is it? Is it a motor or a generator? So here we are saying it's a motor. So if it's a motor, then we know that the electrical system essentially has to pull along the mechanical system. So EF is going to be somewhere down here. So we're going to have EF with this negative delta angle here, and we're going to have IAXS over here, right? So we want to find the complex value. Now we want to get the power factor, so we need to find I, right? So if we look at this here, this is VT, EF, and this is IAXS. So we know for the motor operation that Vt is equal to EF plus IAXS, right? So we have EF. We need to find the complex value. We know the magnitude. So EF is equal to the magnitude of EF multiplied by cosine negative delta plus j sine negative delta, right? So you'll see that's what we do down here. Magnitude of EF by cosine negative delta plus j sine negative delta. And remember, that is negative because it is motoring. And if it was generating, the delta would be positive. Good. The motoring, if you go back to the notes, you'll see that the motoring and the generating does not have to do with whether the EF is larger or smaller than the terminal voltage. That will determine the power factor. Whether the power angle is positive or negative, that is tied to the motoring or generating action, right? So we work out the complex value of EF. Of course, the complex value of Vt is the same as its magnitude because the angle is 0. So we could work out Ia, which is simply Vt minus EF on JXS, and that works out to this value here, which has a magnitude of 744.63 and an angle of negative 51.76. Good. So, and you can see that the angle works out correctly because I has to be somewhere down here in order to get that. It has to be negative in order to give that value of Vt, right? So we have the angle of I now, and to find the power factor, we know the power factor is the cosine of the difference in angle between voltage and current. So it is cosine theta V minus theta I. Which theta V? Which voltage are we looking at? The terminal voltage. Right? That is the voltage we're looking at. So cosine angle of Vt minus angle of Ia, and that gives us a power factor of 0.62. And now that's the end of this question. And we go on to the last question. Good. So for the last question, we have the load of an industrial plant is 40 megawatts at 0.85 power factor lag, and we're using a 2 megawatt synchronous motor to improve the power factor of the plant to 0.95. The motor is rated at 5 kV and has a synchronous reactance of 5 ohms. The equivalent field voltage of the machine can be expressed by EF is equal to 200 IF. So that just tells us how much current we need to give the magnitude of the field voltage. And we're going to assume the motor is running unloaded with 0 rotational losses. So in other words, P is equal to 0. We are only going to have Q. And we want to compute the excitation current required to improve the overall power factor. So this is essentially the same sort of problem as you would have had in ECNG 1000 when we did power factor correction. So we're going to go about it in the same way, except instead of looking at a capacitor, we're going to look at the synchronous machine. So we're utilizing a motor, right? The motor is connected to some load. So just to give you some idea of what this would be like, we would have from the supply, we would have a synchronous motor connected here, and then it is connected to the load, and the load would be 40 megawatts at 0.85 lag. So you would see that normally for the power factor correction questions you'd have done before, we would have placed the capacitor in parallel with the load here. So we're doing the same thing now, except we're placing the synchronous machine, right? And it is rated at 5 kV. So the terminal here is 5 kV, right? So let's simplify this. We have, bring it back to the way we're accustomed seeing it, right? So we have 5 kV here. Good. And right, so and this is EF, and here we have 0.5, so 5 on root 3 here. Good. So we want to compute the excitation current required to improve the overall power factor, and then draw the phasor diagrams and so on. So we define here first our plant power, which is 40 megawatts. Our power factor here is 0.85. Terminal voltage 5 on square root 3, 5 kV on square root 3, and our power factor, our synchronous reactance, which I think I probably had wrong. So it's 5 ohms, not 0.5 ohms. So here should be 0. Here should just be 5 ohms. Good. Now, how did we approach this in circuits? Remember what we had to do was we have our old power factor and our new power factor, and our power, our real power P, which is the power we want to get to the load. And in this case, it is 40 megawatts. And that was being delivered at some power factor with some Q, right? And that was being delivered with cosine inverse of 0.85. And now what we want to do is we want to bring that down to a new value which has a power factor of 0.95, cosine inverse 0.95, right? Which means that this here is the Q that that must go into the synchronous motor. So we have here the S of the plant, and then we find the old Q, so which is the square root of S squared minus P squared, right? This is S squared minus P squared, which will give us the opposite side here. So we have the old Q, then we have the new Q, which we could find the new Q angle, and we could find the new Q from the power and the new angle, and then we could minus them to find what is the value that should go to the synchronous motor. So old Q minus new Q gives us 11 megavars, 11.6 megavars approximately of Q that must go to the synchronous machine. Good. So now we need to find what is the excitation current required. So first we have to figure out what is going on here in the machine. So we figured out the old Q and the new Q. We figured out how much Q must go to the machine. And now we want to see what is happening with the synchronous machine. So we have Vt. We're going to go back to our phasor diagram. In this case, I, because it is completely reactive, no real power, right? All the current is reactive. It would be at 90 degrees to the voltage. And IA, so this is IA here, and IA excess is going to be here, which means that EF is going to be somewhere over here. So EF plus IA XS is going to land us at Vt. So this is the situation that we have. So let me just remind us of what we are trying to find here. The excitation current. Good. So we want to find EF. So we need to get EF, and we have the angle of the current 90 degrees. We know we want to find Q. So we have an equation that gives us, that relates the voltage Vt, EF, and the power angle delta to Q, right? So we have these two equations. One is P is equal to 3 Vt on XS by EF sine delta, and the other is Q is equal to 3 Vt on XS EF cos delta minus Vt. So what do we have? We have Vt, we have we don't have EF, we have delta, we have XS, and we have Q. So we could calculate from that what is the value of EF. So that is what I have here, right? So Q multiplied by XS over 3Vt plus Vt will give us EF. Of course, delta here is 0 because there is no power, right? So you'll see it lies, EF lies right along Vt. So delta is 0, so cosine 0 is 1. So that is why we don't have the cosine delta in the equation here. And from that we could work out EF to be 9.6 kV. Good. And now we know the value, we know the relationship between the field current and EF. So we could work out EF as, let's see what it was. We could work out EF as, what was the relationship? 200 IF, right? So we have 200 IF, and that gives us, so if we want to find IF, we just divide 9.6 by 200. IF is equal to 9.6 kV on 200, and that gives us 48.04 amps as our field current. Good. Now, the rest of the questions ask us to draw a phasor diagram showing the relationship between the armature current terminal voltage and excitation voltage. That's actually what we did here. So we did that already. And we want to show now how would the phasor diagram change if we do have rotational losses, which would actually be the situation, and what effect would that have on the reactive power absorbed. So to do that, we're going to have to look at our equations here. But let's look at first what is going to happen. Now, if we have VT and we have some rotational losses, it means that we're not going to have a zero power angle. Now remember, we have P is equal to 3VT on XS EF sine delta, and Q is equal to 3VT on XS EF cosine delta minus VT. Good. So now, before delta was 0, which made this entire P 0. Now, if P is not 0, it means delta will no longer be 0. So here's our VT. And which direction would the power angle go? Since it's a motor, then it would be negative. So we're going to have some EF here, right? So we're going to have some delta. Now, what is going to happen? If we have some delta, what is the effect on the Q? If we have some positive delta here or some negative delta, some non-zero delta, remember this is your graph of cosine. So previously at delta 0, you had 1. Now you have some non-zero delta. So you're going to get some value here less than 1. So if you get a value less than 1, this entire thing is going to be reduced and your value of Q is going to go down. So you're going to have less Q. So what could you do? What would you have to do in that case? You would have to simply increase EF, which would mean increasing the value of your field current. Okay, so that's it. If you all have any questions, please feel free to contact me. You could write on the forums and so on. You could email, and let's get things sorted out if things are not clear. I will also put up the group project today, and put up the group, so you should start looking at that as well. Okay, so that's it for the synchronous machine tutorial.